Okay, before we solve problems, let me explain the direction of torque. Torque is a vector quantity, therefore it has direction. If it's clockwise, if the rotation is clockwise, so the torque is negative. But if the rotation is counterclockwise, the torque is positive. Let me explain why. If, for example, you have here a wood and then the fulcrum is at the center, then you exert a force at this point. Take note that we have torque Fd sine theta, but if sine is 90, that is equal to 1, so that is just Fd. We have here the force is downward, but the lever arm, the D, is positive. And then if you're going to push this, the rotation will be clockwise. Negative times positive, that's a negative torque. Another illustration is this. If again you have at the center the axis of rotation, and then the force is exerted here, it's like you're pulling it upward. Now you can see here that the force is positive, but the lever arm is negative. And then if you're going to pull it, the rotation again will be clockwise. So that means there is a negative torque. Now take note that if you have a clockwise rotation, that's a negative torque. And then for the explanation for the counterclockwise torque, we have here. Okay, again, the center is here, or the axis of rotation is at the center. And then you have a downward force here. You can see that the force is negative because it's downward, but the lever arm is negative. You will have a positive torque. Okay, you will have a positive torque, which is the rotation is here. You can see that it's in a counterclockwise direction. Another illustration is this. You have here at the center. And then this one, you try to push it upwards. Now, if you will pull it upward, you will see that the rotation again is counterclockwise. The force is positive, the lever arm is positive. Therefore, you have a positive torque. Okay? And that rotation is counterclockwise. So that is a positive torque. Okay? Now, let's try to solve. Okay, let me also discuss about the second condition of equilibrium. In the first topics that we had the first condition of equilibrium, wherein the summation of forces is equal to 0. But for the second condition of equilibrium, the summation of torques is equal to 0. So a positive torque, the torque on one side is equal to the torque on the other side, so that they will sum up to 0. That is the second condition of equilibrium, wherein we are going to apply this in the next problems. Okay, let's have the first example. The woman, mass M, sits on the left of the seesaw. The man, mass M, sits where the seesaw will be balanced. Apply the second condition of equilibrium and solve the unknown distance x. So this is the distance. You can see here again, this one will cause a counterclockwise direction. So there's a positive torque. We now have torque 1 should be equal to the torque on the other side. So here, this is the mass. Let's say that the mass of the girl, let's have the mass as 40 kilograms. And then for this one, let's have his mass as 55 kilograms. So you have here torque 1 equals torque 2. Let's have torque 1 is the torque caused by the weight of the girl. So you have here the force 1, and then the distance 1 is equal to the force 2, and then the distance 2. What we are trying to look for is the distance 2. So let's divide everything by F2. Okay, we now have a final equation wherein distance 2 is just equivalent to F1 D1 divided by F2. Then let's just substitute. Since the given is mass, so we still have to multiply it by acceleration due to gravity. So the mass is 40 times 9.8. And then the distance here is 2 meters. So let's just use 2, no need to convert. Then divided by the force, which is 55, multiplied by 9.8. Okay, so let's solve. Okay, now the answer is distance 2 is equivalent to 1.45 meters. So you can see here, if we are going to analyze it, since this one has greater amount of force, to produce same amount of torque, it has to have a lower lever arm, okay, or a shorter distance, which is equivalent to 1.45 meters. Okay, next problem we have here. Calculate the force that the biceps muscle exerts to hold up the forearm and the book shown in the figure. Compare the force exerted by the biceps muscle with the weight of the forearm and the book. Okay, so let's analyze now the torques produced here. We have here the axis of rotation is this at this point, triceps muscle. Therefore, any force exerted on this will not cause rotation since this is the axis of rotation. And then you have here the biceps muscle, which is upward because it tends to contract. And then we have here the load and then the center of gravity. If you can see here, if you will analyze, we have here the torque produced by the biceps muscle. It's upward, so that's positive, and then the lever arm is positive. If you will analyze, the rotation caused by this one is counterclockwise. So that is positive torque. Then for this one, the center of gravity is downward. This is the axis of rotation. Therefore, the rotation is clockwise. So that is the negative torque. The load added also here will cause a negative rotation or a clockwise rotation. Therefore, it's a negative torque. We have here the positive torque is equal to the negative torque. So I will place the counterclockwise torque here. Torque counterclockwise is equivalent to the torque clockwise. What will produce a counterclockwise torque is the torque of the biceps muscle. But the CG and the physics book will cause a clockwise rotation. So let's now have here the force exerted by the biceps muscle. Now you can see here, it's perpendicular. So we can just use FD since the angle is 90 degrees and sine 90 is equivalent to 1. So we now have F of the biceps muscle and the lever arm, which is 4 centimeters. But we have to convert in meters later, is equivalent to the torque of the CG and the distance of the CG plus the torque produced by the book, physics book, I'll use P, and then the distance or the lever arm of the physics book. So let's divide everything by the distance of the biceps muscle, okay? So let's substitute now. Okay, look, we have here force of the biceps is equivalent to the force of the CG, that's 2.5 times 9.8 times the displacement, that's or the distance is 0.16 there. Then plus we have here 4 kilograms times 9.8 times the distance is 0.38 in meters. Then we divide everything by the distance of the biceps muscle, which is 0.04. We have here 2.5 times 9.8 times 0.16 plus 4 times 9.8 4 times 9.8 times 0.38 divided by 0.04. Okay, our answer is the force of the biceps is equivalent to 470 newtons. Okay, so our answer is 470 newtons. Now, if we are going to compare that to the mass or to the force exerted by the CG and by the physics book, let's solve. Let's compare it to the force of the load. We have 4 times 9.8 plus the center of gravity is 2.5 times 9.8. The total load, okay, the force exerted by the load is actually equivalent to 63.7 newtons. So you can see here that with that particular load that we have here, the biceps muscle has to exert great amount of force so that you can balance it. Okay, so there is a force, or there's a tension in your biceps muscle amounting to 470 newtons to balance the arm holding the physics book. Okay, considering the center of gravity or the mass of the arm we have and the mass of the physics book, their weights are equivalent to 63.7 newtons, which is small compared to the force that the biceps muscle has to exert. Because as you can see here, there is shorter lever arm for the biceps muscle. That's why it has to exert greater amount of force to keep it balanced. Okay? So that the second condition of equilibrium is satisfied. Alright? Next. Okay, for the next problem we have here, calculate the force exerted by the extensor muscle in the upper leg. Okay, so that's the system when lifting a weight as shown in the figure. So you have there 10 kilograms. Take note that this tension, the weight, will be translated as tension here. So that tension is equivalent to the weight, which is equivalent to mg, or 10 times 9.8. Okay, so we have here, this is the axis of rotation, that's the pivot. Then we have here the force exerted by the extensor muscle, and then this is the tension. What we are trying to look for here is the force exerted by the extensor muscle, Fm. Okay? If this is our pivot point, and you can see here the direction of the force, so that will cause a counterclockwise direction. So it will produce a counterclockwise direction. So we have here the torque, again counterclockwise, is equal to the torque on the other side, which is clockwise. In this problem, we have here the tension, which will produce, if you're going to analyze it, it will produce a clockwise rotation. Okay, so let's now substitute the given we have here. For the counterclockwise rotation, we have the force of the muscle, and then the lever arm, the R, the distance of the muscle, is equivalent to the tension, and then multiplied by the distance of the weight. So we have the force of the muscle, we are looking for that, equals the tension times the distance of the weight divided by the distance or the lever arm for the muscle. So we now have here the force is, tension is mass times 9.8 mass given is 10, so that's 10 times 9.8, times the distance of the weight, that's 35 centimeters, so you have to convert it to meters, it's 0.35 meter. Then divide everything by the distance of the muscle, which is 2 centimeters, that's equivalent to 0.02 meters. Therefore, we now have 10 times 9.8 times 0.35 divided by 0.02. Here, our answer is 1.715 times 10 to the third, or that's equivalent to 1,715 newtons. Okay, that's the force exerted by the extensor muscle so that it will be balanced, or so that there will be no rotation. Okay, so that's our answer. Now, looking at this again, comparing it to the weight is only 10 times 9.8. So that is only 98 newtons. But the extensor muscle has to exert a force amounting to 1,715 newtons. Okay? So that's why with that exercise, pwede lumaki yung muscles. Okay, next item. Okay, next we have here, even when the head is held erect, so you can see there, its center of gravity is not directly over its major point of support. So the major point of support is the pivot point, which is here, there. But the center of gravity is at the distance from that point. Its major point of support is the atlanto-occipital joint. The splenius muscle in the back of the neck must therefore exert a force to keep the head erect. Calculate the force they must exert if the mass of the head is 5.0 kilograms. Okay, so this muscle, the splenius muscles at the back, should balance this torque produced by the weight of the head. Okay, so let's now solve for this one. Okay, so let's analyze this one. The center of gravity, it will produce a clockwise torque, so that's negative. And then this one will produce a counterclockwise torque. So that's positive. You imagine pulling this one, so ang ikot niya is counterclockwise. Okay? But you imagine pulling this part, ang ikot niya is clockwise. That's how you identify. We have here again the torque and the counterclockwise is equivalent to the torque clockwise. Okay? So that the sum is equivalent to 0. We now have here Fm, which is the force exerted by the splenius muscle. Okay, that's the force exerted by the splenius muscle. And then the distance or the lever arm of that muscle equals the force of the weight or the center of gravity, and then the distance of the center of gravity. So if we are looking for Fm, it's just Fm equals the force of the center of gravity or the weight of the head, the distance of the center of gravity, divided by the distance of or the lever arm of the splenius muscle. The force now is 50 newtons, so that's 50 newtons, times the distance is 2.5 centimeters, so convert it again to meter, that's 0.025. 0.025 meters divided by the distance now of the muscle is 5 centimeters, so that's 0.05. There. Okay, again, that's 50 newtons times 0.025. Okay, our answer is 25 newtons. We have here the force to be exerted by the muscle is 25 newtons. If we are going to compare it again, the head is 50 newtons, but the force that the muscle has to exert is only 25 newtons. So looking at this one, we are very lucky that the lever arm for this one is longer compared to the lever arm of the head. That's why the muscle has to exert a smaller effort to balance the torque produced by the center of gravity of the head. Okay. So though there is still a muscle pain, that pain, okay, that the force exerted by the muscle is not that much compared to the force or the weight of the head. Okay. Okay, let's have the next item. In the figure, a pole vaulter carries a 6.0 meter long pole by pushing down in his right or with his right arm and up with his left hand. The pole is uniform and has a mass of 10 kilograms. Find the forces at the left and at the right. We are looking for FR and FL. So how do we solve for that? Okay, now let's take a look at this first. Let's assign an axis of rotation. Let's have FL to be the axis of rotation. Okay, if you're going to imagine, you're holding a pole and then that could be an axis of rotation, it may rotate at FL. So let's consider this point first as the axis of rotation. Okay, with that, we can consider that this force, this one will cause a counterclockwise rotation, that's positive, and then the CG will cause a clockwise rotation, which is negative. So let's now solve for the torque produced by them. Okay, you have here again torque at the counterclockwise is again equivalent to the torque clockwise. You can also use torque 1 and torque 2. So for the counterclockwise, we have Fr, or the force exerted by the man at the right. So that's Fr. And then the distance, or the lever arm, Fr, is equivalent to the torque clockwise. So that is the force of, or the weight of the pole. That's the weight of the pole. And then you have the distance of the weight, or the distance of the center of gravity. Okay. Now you want to look for the Fr. So we now have Fr is equivalent to the force or the weight of the pole and then the distance of the center of gravity of the pole divided by the distance of the force at the right. So let's substitute everything now. For the force of the weight of the pole is, it's 10 kilograms. So that's 10 times 9.8. And then its center of gravity, its center of gravity from the axis of rotation is not 3 meters, but 3 minus 1 meter. So that is only 2 meters. That's the distance from the axis of rotation. Then divided by the distance of the right force from the axis of rotation. So this is 1 meter minus 0.3. So that's equivalent to 0.7 meters. Okay, solving for it, 10 times 9.8 times 2 divided by 0.7, the force at the right hand should be equivalent to 280 newtons. Okay, so that's our answer. The force at the right is equivalent to 280 newtons. How do we solve for the force at the left? Okay, there's a correction in the problem. It should only be 3 meters, 3 meter long pole. Okay, so let's now solve for F at the left. With that problem, we can now consider this point at the end as the new axis of rotation. If that is the case, okay, let's analyze again. If that's the new axis of rotation, okay, let's analyze that. This is the axis of rotation. This will cause a clockwise direction, so that's negative. This will produce a counterclockwise direction, which is positive. Okay, this one will produce a clockwise direction, which is negative. Okay, so we just have to solve it so that we have torque counterclockwise again is equivalent to the torque clockwise. So the one which will produce a counterclockwise torque, or you can just have the summation of torques. Okay, this one is a counterclockwise torque, FL. So we have FL. Then the distance, L, equals the force at the right and the distance at the right. And then you have here plus the force of CG times the distance of CG. But what we are looking for here is FL. So let's divide everything by DL. Okay, now let's substitute. The force exerted by the right, we were able to solve for it. That's 280 newtons. But the distance from the axis of rotation, it's not 0.7 anymore, but it's 0.3. Plus the force of the center of gravity, the weight. Okay, the weight is 10 times 9.8. So that's again 10 times 9.8 times the distance is from the axis of rotation, that's equivalent to 3 meters. So that's 3. Then divide everything by the distance of the left from the axis of rotation. So this distance, that is 1 meter. Our answer is 280 times 0.3 plus 10 times 9.8 times 3 divided by 1. The force exerted by the left arm is equivalent to 378 newtons. Okay, so our answer is 378 newtons. So that the pole is in equilibrium. Okay, I wanted you to solve this one. A man stands on his toes by exerting an upward force through the Achilles tendon. Calculate the force in the Achilles tendon if he stands on one foot and has a mass of 80 kilograms. The next item, what force must the woman in the figure exert on the floor with her hands in order to do a push-up? So you have here the center of gravity, or the weight. So that's the mass times the acceleration due to gravity again. This is the force that the woman has to exert. So you have to solve for that. And consider the feet as the axis of rotation. Okay. So you have to get the distance from this point. Okay. So solve for the force exerted by the woman. Okay, that's it for your exercises. Try to solve those. And then just send me a message if you have any question. Okay, we'll end with this problem solved.